All right. Just because something satisfies Bragg's law, it doesn't necessarily mean that it's going to diffract, right? Why is that? Well, consider FCC versus BCC. Both of those are cubic, but they might have different peaks because they have atoms in different places, right? One has atoms on the face centers, other is body centered. They both have them on the corners. So we need to take into account where atoms are located. In this class, we're not going to figure out how to do that. That's a course for materials characterization, which you hopefully will take later on. However, in this class, we will give you some basic rules for a few things. For example, we're told the following, that a BCC lattice will only have diffraction under the following condition. First off, Bragg's law has to be met, and then when you have Bragg's law met, H plus K plus L has to add up to an even number, right? For FCC, we're told that H, K, and L must be all even or all odd. Okay, so those are two examples of some additional diffraction rules that have to be in place in order to observe diffraction. Okay, with that, let's do an example. So, consider this question. FCC gold has a lattice constant of 4.078 angstroms, so we know the lattice constant of gold. It asks the following question. At what 2 theta value would you observe the third peak starting from 2 theta equals 0 if you were using copper K alpha radiation, which has some value, 1.54056 angstroms? So it's asking this question, right? When you measure intensity versus 2 theta, you're going to get peaks occurring in your sample. It wants to know what will be this one here, the third one, right? The third smallest 2 theta value. Okay, we can answer that question. How do we get started? Well, the first thing we should note is that it said it's FCC. Therefore, it's FCC. That means it's cubic, and we will only get diffraction if H, K, and L are all even or all odd. So, what are the candidates that it might be? Let's make a list of possible H, K, L values. H, K, and L. So, if they're all even or all odd, it might be things like 1, 1, 1, maybe 3, 1, 1. How about 3, 3, 1? It might be 0, 2, 2, or maybe even 0, 0, 4. I'm just brainstorming numbers starting with low values and then increasing. We'll show you why in a moment, right? Now, what else do we know? We know the following. We know that lambda is a constant equals 2 times d multiplied by the sine of theta. Therefore, since this is a constant, if we want this to be the smallest values possible, we want this to be the largest values possible. Okay? So, how do we know what that will be? Well, we know the following, that 1 over d as a function of HKL, 1 over d squared, since it's cubic, that's equal to h squared plus k squared plus L squared, dividing this by a squared, right? Therefore, if we want to have the largest interplanar spacing possible, we want the smallest value right here, right? So if we add up h squared plus k squared plus L squared, we want it to be as small as possible. So let's do that. H squared plus k squared plus L squared, for all of these, let's figure out what that's equal to. Here, it's going to be equal to 3, equal to 9 plus 1 plus 1, so 11. Here it will be 19. This one will be 4. This would be 8. And this would be 16. So again, if we want to figure out the third smallest reflection, assuming that we got all the possible peaks here for a minute, the third smallest reflection will happen at the third smallest 2 theta value will be the third smallest h plus k plus L. So the lowest one is the 111 peak, the second lowest would be the 002 peak, and the third one looks to be the 022 peak. So we would expect it to be this one right here. Let's double check and see if we got this right. When I come over here to the FCC structure for copper, right, we can go ahead and we can simulate the X-ray diffraction pattern. If you don't know how to do that, you can, I'll show you how real quick. You come up here to Utilities, go to Powder Diffraction Pattern. We're going to calculate it. First, we're going to set some conditions, make sure that the copper radiation is selected. So great, let's hit Calculate, and here we have it. So here's the first reflection happening at the lowest value of 2 theta at 43 degrees. You'd expect to see the 111. The next peak is going to be the 2, 0, 0, and then the 2, 2, 0. And this is exactly what we got, the 1, 1, 1, followed by the 0, 0, 2, followed by the 0, 2, 2. Now, is 0, 2, 2 the same as 2, 2, 0? Of course it is. They're in the same crystallographic family, right? They're both members of the family 2, 2, 0, right? So they are equivalent with one another. Therefore, that's how you go about using Bragg's law to calculate what peaks will be at what location. In this case, we figured out which one will be the third one, and we never actually had to calculate what value it would occur at. We just figured out which would be the third smallest by figuring out the third smallest sum of h squared plus k squared plus l squared.